Okay, so we're going to talk about electromagnetic induction before you can do the lab. So this electromagnetic induction was discovered by Michael Faraday and also Joseph Henry. When they did the experiment, they found that when you have a current go through, when you have the bar magnet that passes through the coil, what happened was that there's a current generated within that coil. So the equation for the Faraday's law of induction is this. So this is the induced amp, which is equivalent to the voltage. That's equal to negative N and then d phi b dt. So what is d phi b? D phi b here is what we call the magnetic flux, and which can be calculated using this. So it's basically the magnetic field through the cross-section area dA, and you just integrate that. That gives you magnetic flux. So what this equation tells you that if there's a change of magnetic flux either through the change of magnetic field or through the change of cross-section area or through the angle between the magnetic field and the cross-section area, then there is an induced amp in the circuit. When there's an induced amp in the circuit, it means that there's induced current in the circuit. Now the N here, the capital N here, indicate the number of turn, of that coil. And what does that negative sign indicate? That negative sign can be explained by the Lentz law, which means that the induced current in the circuit will oppose the change, in the circuit. So this is what we call the Lentz law. And in short, it means that nature does not like to change. When there's an increase, then the induced current will have to be in the direction to oppose a further increase. And if there's a decrease in the current, in the magnetic flux, then there's an induced current to compensate for the loss. So this is what we call the Lentz law. And this equation is what we call the Faraday's law of induction. So in terms of the phenomena, so these are the equations that we have, and this is the magnetic flux. So as you can see, in order to have electromagnetic induction, the key parameter that you should be looking for is the magnetic flux. If the magnetic flux increases, what's going to happen is that the original magnetic field of the circuit and the induced magnetic field in the circuit, there has to be in the opposite direction. Okay? And if the magnetic flux decreases, then the original magnetic field and the induced magnetic field, they have to be in the same direction, just to compensate for the loss. Okay? So these are the guidelines or the laws to abide when you want to determine whether the induced magnetic field is in what direction in relation to the original magnetic field. So I'm going to give you some example. Let's say you have a circuit or a loop with no current initially. So let's say this is the cross. So you have the loop like this. I'm just going to look at the front view. So this is a section of the current loop. No current. So this is a loop. I'm just drawing the front. Front view, the top view. Okay. So let's say you have a bar magnet. And the bar magnet, let's say you have the north pole that's facing this loop, and so this is your south pole. So if you have the south, so the directions of the magnetic field is from the south to north. So you will draw a line to indicate that's the directions of the magnetic field. Okay, from south to north. And then you have this current loop, but there's no current inside the in the loop as of now. So now what I'm going to do is I'm going to bring this bar magnet toward the loop or away from the loop and see what will happen. Okay? When you move this, so this arrow indicates that's the directions of movement. So this is the motion, indicating the motion that's going in this direction. When this bar magnet is closer to this current loop, we know that magnetic flux increases, right? Because you have more magnetic field line passing through this cross-section area of the loop. If by Lentz's law, and also by Faraday's law of induction, if the magnetic flux increases, which means that the original magnetic field and the induced magnetic field has to be in the opposite direction. In what direction would the induced magnetic field be? That would be in the opposite directions of that. So the induced magnetic field will be in this direction. That's opposite direction. So I will use IN to indicate that's induced magnetic field. So once you have the induced magnetic field that's in that direction, which is within that current loop, which means that the induced magnetic field by the movement of this bar magnet will be in the leftward direction. Once you have the leftward direction identified, then use your right hand rule. So your thumb indicates the directions of magnetic field. Your curved finger gives you the directions of the current. So in this case, the induced current direction will be in this direction. So you will draw a line like this. So that will be I induced. Okay? So that gives you an example that when you have a bar magnet with a magnetic field that's pointing rightward, with the motion that's rightward as well, then magnetic flux increases. When the magnetic flux increases, induced magnetic field that is in the leftward direction and that's in the opposite directions of the original, and use the right hand rule to deduce the current direction, and you get that. What about if I move this bar magnet away from the current loop? So I'm going to do, so you still have the bar magnet that's pointing in that direction, but now the motion now is in the leftward direction. If the motion is in the leftward direction, which means that magnetic flux decreases, because you have now magnetic field lines passing through this cross-sectional area. So when the magnetic flux decreases, it means that you have the B and the original. The B original and the B induced, they have to be in the same direction to compensate for the loss. So in that case, this is the original direction, so you have to have the induced magnetic field that's in that direction, in the same direction as the original, in order to compensate for the loss. And then once you determine the directions of the induced magnetic field, use the right-hand rule. So your thumb is the directions of the induced magnetic field. Your curved finger gives you the directions of induced current. So you have now your current changed direction. So now this is the directions of induced current. Okay, so this is one example when you have a bar magnet with a magnetic field that's pointing rightward. You have the motion that is to the left and to the right, and that can produce different results, and in such a way that the induced magnetic field will be different, and the directions of the current will be different as well. We can do another one, with the bar magnet that we flip in the bar magnet. For example, so now we have a current loop like this. We can have the bar magnet. Now we have the south pole here, the north pole here, so the magnetic field is in this direction. Okay? So the motion, now I'm going to bring this to this current loop. So this is the directions of my motion. When you have the directions of motion, that as you can see, even though the magnetic field is pointing in that direction, but it is moving toward this current loop. So this indicates that the magnetic flux increases because it is you're bringing this bar magnet toward this this loop. When you have the magnetic flux increases, it means that magnetic field and the original magnetic field and the induced magnetic field, they have to be in the opposite direction. So this is the original direction. In the opposite direction, meaning the induced magnetic field has to be in this direction, just so it is in the opposite. And then use the right-hand rule to determine the directions of current, and you see that your fingers follow the counterclockwise rotation. So this is the directions of the induced current. Okay. Now we can have another. We can also move this bar magnet away from this current loop. So you still have the same bar magnet with the same magnetic field orientation that's pointing leftward, but now I'm going to move it to the left. So this is the directions of my motion. And as it's moving away, we know that magnetic flux decreases. When magnetic flux decreases, it means that the original magnetic field and the induced magnetic field, they have to be in the same direction to compensate for the loss. So in that case, same direction, meaning that will be in this direction. So now your induced magnetic field is in the leftward direction. Use the right-hand rule, then your current direction will be in this direction. Okay? So that's basically, once you know how it works, then you're ready to do an experiment. Now, before that, there's an assignment I want you to do. I want you to complete the section on page 8-7. And, excuse me. So I'm going to do the first one. So the first one, so let me just draw the diagram right here. So do the full arrangements on page 8-7. Okay. So you have the bar magnet. This is a solenoid. So you have a solenoid and with the current, with the loop that's winding in that direction. And this is a bar magnet. And this white dot indicates that's the north pole, okay? And you're asked to find, and the motion of this bar magnet is to into the solenoid. So you're asked to identify the directions of induced current, the directions of induced magnetic field, and so forth. So the one written in red will be the one that I asked you to do, okay? So you have the north pole here, which means that you have the south pole there, meaning that your original magnetic field is in this direction, okay? And this is the directions of the motion. So in that case, when you have when you bring the bar magnet toward the solenoid, you pretty much increase the magnetic flux. So I want you to write this: magnetic flux phi increases due to the motion that's inserting into the solenoid. When the magnetic flux increases, it means that the induced magnetic field has to oppose the original. Okay. So if you have the, if the directions of the magnetic field is in this direction, it means that the north pole is here and the south pole is there. Okay. So you can see that you have a north pole facing the north pole, so it's a repulsive. So that's why oppose the further, increase. Once you have the directions of induced magnetic field found, then you can use the right-hand rule, and the directions of current follow the directions of loop. So this is the directions of the induced current. So this is what I want you to do. There are 3 other ones that you have to do on page 8-7. So all the things that are written in red are the one that I asked you to do, and then you have to show me, when you come in to do a lab. Okay? All right.